Hello, and welcome to this presentation on NSO-ARC. My name is Mikael Tidemar, and I'm a customer delivery software architect at Cisco. So, you have an NSO project, and you're going through the manual testing phase. So the manual testing phase will remain the same, more or less the same in all projects. But after the manual verification of the actual configuration is what you're expecting it to be in the network devices, comes the automation part. So test case creation is generally not an automated process. There is manual configuration capture, there is a manual test case file you need to write, as well as, of course, the test case definitions. So any service update will require at least a new configuration capture, if not a rewrite of the actual test case itself. So how do you actually deal with the variations during a project? How do you deal with upgrades? How do you verify that the configuration is pushed the same in different environments? And how do you actually deal with the agile sprint development methodology changing the actual expected results of your tests? This means that automation engineers spend a lot of time on manually creating and updating existing test cases. So for a very real and case study we did for a customer, a service provider in the EMEA region, we spent a lot of time delivering automated test cases in an L2 and L3 VPN project. So basically we met with the developers, we discussed the packages, and then we developed the first version of all tests, like all variations of tests. Then we went back and discussed packages again, we changed the tests, and all of this consumes a lot of time. Then we find an issue, we explain the issue to the developers, and then we get the fix eventually from the developers. Then we debug the code again, we find something wrong, and we change the test. Then comes another iteration with another problem. And then when we are done with that, we ran the tests in the customer device lab, and we of course found another issue and had to rerun it. So another 3 hours used. That's totaling 15 hours for fixing a single use case for the customer in the network. So that's the old way. With NSO-ARC, we can get this down to around 2 hours and 17 minutes. Doesn't that sound perfect? Basically, we configure the service instances in NSO based on the inputs from the developers. Then we add some more creative variations to that. Then we run the tool, NSO-ARC. Then we feed back to the developers. And then we get the new fix again, change the service, and rerun NSO-ARC. Then we have 10 minutes of reporting an issue. Then we get another fix. Then we rerun NSO-ARC. And then, of course, at the end, we have another iteration with a new problem. In the end, we spend around 1 hour with the customer in the actual device lab. We are using the test cases generated by NSO-ARC, and that's very fast. And most of the time then is spent actually interacting with the customer. So we are actually introducing an automated quality assurance approach for NSO projects. And we do this without additional time budgeted, with or without a CI/CD pipeline setup, and without learning robot. And we don't need any specific test planning in advance. can it be done? Of course. NSO-ARC. ARC stands for Automated Robot File Creation, where we're using NSO and the robot framework. So what do I get from NSO-ARC? So you get your configured service instances in your CDB, which are already manually verified, turned into automated test cases using create, read, update, delete in a matter of seconds. And these are simple robot framework tests using well-established standards like RESTconf. NSO-ARC is an action package. It is, of course, CI/CD pipeline addressable with a northbound interface like any other NSO package. It is roughly 2,000 lines of code. There are Python files per actions and some helpers. It has fast execution, it's pretty scalable, it supports large-scale architectures, multi-layer stacked services, and nano services. It is compatible with NSO 5 and 6. It's used in CX in delivery in multiple ongoing engagement today. However, it does not support reactive fastmap or kickers. NSO-ARC is a unique tool, and it's unique in its capturing capabilities. It works with the live status execution of show running config, or actually RPC request shall execute through the NED. It gives you a line-by-line configuration validation, which is unfiltered by the NED. It does give you a diff comparison between the before and after configurations, which means the similar results can be compared in lab, any development lab, and pre-prod or production environments. NSO-ARC consists of actions. So the ARC action has some unique input methods, like create robot takes 4 different input possibilities. The 4 input possibilities are all service instances, which basically takes all your configured service instances in your CDB and turns them one by one into test cases in robot. Then you have an option of doing service type, where you would input the service points which you're interested in generating tests for. Or you can go and pinpoint the actual service instance, giving the specific key path to your service instance to enable you to have very fine-tuned options for this specific service instance. There are also some very handy keywords to use. No networking, of course, it does exactly what you expect it. You don't touch the network devices when you generate the test cases. This does limit you to only the NSO worldview of what is configured in the network. Then we have test in isolation, which means that each and every service instance in your system will be tested in isolation, which means we're deleting all other services before we test one by one every service instance in isolation. This comes in handy if you have cross-service configurations where multiple services are actually configuring the same devices and in the same locations on the configurations. Then we have include children, which actually allows you to include testing of children of a stacked service. This is not generally recommended, but we give you this option anyway. Then we have the keywords of pre-config CDB and pre-config devices. Pre-config CDB actually allows you to give XPaths inside the NSO CDB, which you need to capture and pre-configure in your lab environment or your development environment before you run the actual test cases. And And if you need also to pre-configure the devices, you can capture the pre-config for any device names in a list, which will then be applied before the test cases are run in robot. Then, of course, you have this mandatory output path keyword, where you would then be able to use absolute or relative path and give a folder name where you want to actually store the test cases. Then you have the fourth option, which is called modify variation. Basically, this gives you the option to modify some or many parameters of your service instances. And you can provide positive and negative modify values in a list for each parameter separately. Each and every positive modify value will generate a test case and configuration for each. Negative modify values are expected to fail, providing the failure option where the payload will actually be rejected by RESTconf. So what does it give as an output? We get, of course, robot files. But we also get a repeatable date and time-stamped folder structure per service instance, with the necessary files generated for validation of the service instances. Then we can also do this other keyword, add to previous. That allows you to create batches with individual options added to a combined service testing robot file. And of course, all of this is 100% ready for implementation in any CI/CD pipeline. And now we move to the demo. In front of you, you see my iTerm screen. Here I have the NSO instance on my local machine. I'm going into the NSO CLI, where I have a number of services instance already configured. Now I can do services check sync, which is a handy command to do, which shows me all the configured service instances in my NSO CDB. Obviously, when NSO-ARC runs as an action, it checks this specific list of service instances and will only apply test cases creation to any service instance which is in sync true. If it's false, we are not able to actually capture a correct configuration for that service, and those are ignored. So if you look at these results, you can see I have a link service, which is one of the example services you can look up in the examples folder, which is provided in the installation folders. This one is example 20 in getting started developing with NSO. Example 20 is a nano service, which is why it's in my CDB currently. You can also see we have stacked service and a number of router static services with different device types. And we of course have an L3 VPN service and some VRF services which are also in the system. So, ARC action. ARC action has a number of nice actions available, like get service instance key paths. I give the keyword all service instances and I run this command. This gives me all the key paths in my system for the same service instances above. This is very handy because now I can copy paste this and target this specific service which I want to use and generate test case for. So I do my ARC action. I do create a robot. I use the keyword service instance and provide my key path. Now I'm going to add another key path of the L3 VPN service. Close the list, and I then provide an output path, a mandatory input. Now I can tab complete and see all the folders in my current location in the actual disk. So I'm just going to make it ARC demo. Now I'm going to run this action and quickly skip to my Atom window. And I can see that my folder has been created, ARC demo. Under this ARC demo folder, you can see that we have a link folder created, and the key parameter is T2. And we have a date and timestamp folder under it. In this folder, we have all the important files like service configuration. This service configuration payload is used to actually create the service instance in your test case. Then we have the before and after validation files, one for each device, and also for the full CDB of NSO. Then we have the devices diff XML, which is actually the get modifications output in XML format. If you're aware of get modifications, you can do it for any service instance in your system and execute it in the CLI. And you will see something similar to this, but not in XML format. This XML get modifications is used to validate the actual configuration of the NSO worldview when always when devices are not necessarily supported by the live status execution, we always get this validation. If we move to the L3 VPN service folder, you can see that again we have a service configuration instance payload, and we have the devices diff for this one with the get modifications output. This modification is done on the iOS CLI and NED, which means in this case we can actually get the line-by-line verification. So we have the before and after CLI files, which is actually the show running config of the actual device. You can see there's a lot. This is a NetSim device, so you can see only the default configuration of the NetSim device. In the after CLI file, of course, we can also see specific configurations for the service instance in here. And then you can see the diff set being generated here. You can see that we are adding these specific lines, All right, what else do we get? Of course, we get the robot file. The robot file contains all the test case definition and all the settings required to run the test case. You can see that we are using the library CXTA, which I'm gonna, of course, discuss a bit later on a slide. But basically, it's CX test automation framework built on robot. We have the Docker run command, which is very handy. And you can run the test case using this. So I'm going to copy this docker run command for later. We have the keywords used in communicating with NSO, which are created in this robot file. And then we have the test cases part. These test cases are creating a service, we are validating the service, and we're deleting the service. All right, so let's go ahead and run this test case. And since we have just generated this test case, of course, we should expect this to just work. There is also a handy symlink created every time I run this tool. So I can just remove the date and timestamp from here and run with the symlink instead. And there you have a small warning, which is notifying everyone that I, of course, have a MacBook with the new M1 ARM processor. And that's something we can just ignore for now. Bear with me, this usually takes a little bit before it starts executing. And there we go. We have the setup, we create the service, we validate the service, we delete the service. Then we go on with the L3 VPN test case. This one takes a little bit longer, and the reason why I'm going to show you in a second. We're opening this log.html, which is provided by this robot execution. In this NSO service testing log, you can see all the test cases and what has been passed or failed. First, we have a setup. The setup basically does to configure the collect forward diff to true in your global settings on your NSO instance. If this is not already set to true, then we create the service using restconf with the payload which we have captured. If the service is already present in your system, we check this and we set a variable. If this actual variable is set to true, we delete the service instance in your system. And in this case, this being a nano service, we are automatically also checking that we have nothing in the system. So deletion, we are looking at finding a zombie. If you know nano services, these come with zombies. And I don't mean literal zombies, but processes of the actual service instance left over when you have deleted it. So we need to check that the zombie is removed, as in checking that we don't find the zombie anymore. And this one, you can see that it failed and actually found a zombie. And then we run this keyword again 1 second later, and we find nothing. Then we can actually go ahead and modify the configuration on NSO to push the payload once again. When we do that, we also wait for the plan to reach the ready state. And that's done with these keywords here. After this, we validate that the service configuration has been pushed as expected using the get modifications for the service. The get modifications of the service instance is then compared with the captured device's diff XML file. After this is all passed, we delete the service, but again, only if the service was not present to begin with. And this is a very important point here, that we are leaving the NSO in the same state as it was before. So if the service already existed, we leave it after we're done validating the test case. If this is a CI/CD pipeline and you're doing it against Docker containers, of course, you don't want to have a service instance left over once you finish the test case. Okay, so moving on to the L3 VPN test case. In this case, you can see that we have a little bit more going on here. Basically, we have deleted the service if it's already present, right? With the REST-conf call, we get the output 204 back. Then we can actually get the configuration of the devices used by this service instance. So if there are many devices, this will be repeated many times. We do live status show running config against the device. We capture the output of that. Then we modify again NSO to create the service instance using the service config.xml. Then we do show running config on each device once more. And then we actually check the diff before and after. And then we compare it to the files in the file system we have stored for the specific service instance. This is very important. Again, we're only comparing the diff before and after. And we're comparing it to what we have captured when we did the actual test case generation. This is important for any number of things, like if the firmware of a network element has changed and the configuration is somehow different after you apply this same service instance. Again, it's very important to have this show running config validate line by line that is actually still the same output in the network device. Of course, once we have done this expected diff comparison, then we also validate the service with the view from NSO using get modifications for the service instance. Then we compare it to the device's diff XML, which was captured with get modifications by the generation of the test case. And then we delete the service instance, but only, again, if the service was not present when we started off. Okay, so how do I know that this works perfectly every time? Let's go and introduce something wrong with my Python code on my service L3 VPN. I go to my packages folder and to the L3 VPN service, which is actually only a template-based service. I will introduce some faults in the template instead. All right, so imagine that I've done some changes here. Let's change the AS number here. And this was unintentional, obviously. Okay. Now I've made a change. I have saved it to my template. Now I go to my NSO, CLI, and I go and redeploy this package. Then I go and redeploy my service, which is under services. And we have the instance, and we redeploy it, and we dry run the deployment. You can see that we're changing this root target from 1 to 6. And we actually have to do the redeploy without the dry run, like so. All right, so now before I even go and apply these configuration changes of my package into a Git environment where a pipeline would grab those changes and run the actual test cases. The run could take, let's say, roughly 20 to 30 minutes to complete, depending on how fast your pipeline executes. And then only then you would find this error. In the best case, the best scenario is that your test case is actually capable of capturing this small change in the configuration. But in our case, we also, of course, have NSO-ARC. So we have our test cases, and I can run this docker run command once more. And this is what I meant by not needing a CI/CD pipeline to actually perform the testing, because this is pre-pipeline. I haven't done some changes and pushed anything to Git yet, which would then possibly affect a number of unwanted changes, right, for the customer. Now you can see that we have failures, of course. So now we go back and open the log. And you can see that we have a status failed on the capturing config diff and creating the service. And then we can dig into what happened, what is the actual fault here. You can see that we're expecting to have this root target, and we have an actual root target by the service, which is this. The worldview of NSO, again, with the get modifications, will show you also that this is incorrect in this case. All right. In the case that this was an actual change you wanted to make, and this is correct, let me go back to my CLI. In this case, you would have to manually go and change your test cases, but of course we have NSO-ARC. I am running the ARC action once more. And we can go back here and look at what happens in the file system. You can see that there's a new timestamped folder and files are being generated right now. Now you can see in the devices diff file we have this change which we introduced. And of course the test cases are, again, the robot file has been generated The symlink has been recreated for the latest one. So now when I go out to my folder again and run the latest test cases, soon we will see that everything is passing. All right, now we have success on all test cases. All right, now that you've seen the demo, you can see now on the screen is the current release. Current release version is 1.0.8.2. And in the timeline, you can see that we've had many new features added along the path. In the future, I hope we can have some CXTM integration where we can create job files and also hopefully refactor the code and add some multiprocessing perhaps. But back to the point of CXTA or CX test automation. So CX test automation framework, which I used as a container to execute against NSO on my local workstation, of course runs also in the Jenkins CI/CD pipelines or through the CX test manager or CXTM, which I just mentioned. Obviously, the CXTA or Siesta framework works with other things than NSO. So even if your aim is NSO here, the CXTA framework is built to also talk to many different devices and functionalities like APIC, DNA Center, Spirent, DNA. You name it, we have something for it, basically. And why do we actually choose Robot for these in Cisco? So Robot is the open source test automation framework, which actually has a quite natural language keywords. This allows for non-programmers to actually do these kind of test cases without learning too much complex scripting. And Robot has a very large ecosystem and a large variety of keyword libraries which are openly available to the public. It easily integrates with Python test libraries and also created by Cisco, like PyATS, which we can reuse and leverage through Robot. So please don't drown in test case creation work and use our ARC. Thank you for listening to this presentation.